So the four key topics here that we will be covering, really, as was mentioned during the panel, that was mentioned for those who attended maybe the tiny pig session earlier. The game is changing. Silicon photonics, the integration of silicon photonics is really changing the way we're going to have to look at things. And the software guys, some of the software testing strategies that have been implemented for the last maybe 50 years may prove helpful. So this is a bit the idea here, and looking at how we can reduce the cost of the quality of the components, so getting reliable components, how we can inspire ourselves by the some of those strategies, and maybe a couple of ideas on how we could adapt that model to the development of the hardware. So to discuss this with me, I'd like to introduce Gabriel Farr, our CTO. Prior to joining Exfo, he was the co-founder of Element AI, a company providing solution based on artificial intelligence. And he also brings to the discussions over 20 years of experience in software development. So hello, Gabriel.
Hello, François.
So if we look at how the telecom game is changing and why we're really making that statement here, if we look at some of the latest market studies, we can see that silicon photonics, if we look at the forecast on how it's going to be used, how it's going to be integrated into the network elements, is really a huge growth over the next 4 or 5 years. But considering that over half of the cost of typical transmission system is coming from the transceivers themselves, not really surprising to see that the biggest growth and the biggest chunk of the pie really, or the first people to use silicon photonics will be the transceiver manufacturers. So this is clearly what we can see there with data center, obviously, considering the number of transceivers involved in the data centers. Not really surprising, but it means that a lot of the transceiver vendors will have to adapt to this reality. So if we look at the overall process, starting to use silicon photonics means that we're going to start the process right at the foundry level, where the foundry will produce the wafer, the dies that will be used in putting together those transceivers, and then all along the way to the commissioning during deployment, there will be some tests that will be performed. There will be some data acquired, and so we need to adapt that process and look at how we can move along the way. Also, considering that over 70%, in fact, of the component based on PIC is coming from the packaging steps and later in the process, opposite to a bit what we're seeing with CMOS and ICs today, means that the earlier we can identify failures or predict failures, the lower our manufacturing cost will be. It's a multi-step process. It's with multiple players involved. So we have to take that into consideration into how we can, bring those identification of failures as early as possible. So one of the issue in doing this, if you go from the foundry to a packaging company to an end user in the process, it's really multi-step, multi-stage. And what we've seen really talking to customers so far is that the end user, the people that really want to market or use those components are really the ones driving the overall process from a communication perspective, data collection, data traceability. And it brings a lot of challenges because it makes first the burden of all the process on one group, and a lot of security challenges around the data, how to exchange data between the people, the different players in the process. So we thought, and we've looked talking to Gabriel at different approaches and realized that software development and deployment, really, they faced similar challenges over the last 40, 50 years. So I asked Gabriel really to talk to us about how they did it, how they got to the point today where they have overcome those challenges. So Gabriel?
Yeah, thanks, Francois. So as you can imagine, this like testing software did not magically happen on a Monday morning, a sunny Monday morning kind of thing, right? So there were many evolution and improvement. And today, what we can see is pretty much standardized and well accepted in the industry of software development. They are from everything from the smaller, faster, very isolated and cheap unit test where you could have millions of them in a big system, and down to the end-to-end system tests that are much slower, larger, needs a lot of integration, potentially human intervention in the testing flow and everything, and much more expensive. So as you can see from this pyramid here, you will want to put much more emphasis initially in the smaller, faster, and cheaper tests than waiting till the end to do the end-to-end testing, because it's much longer. The feedback loop is not as fast, and you want the fastest, quickest feedback loop as possible.
Okay. And what you're saying, Gabriel, and it makes me realize that we can really associate with you're identifying, for example, at unit test, it's really what we're seeing at the wafer level or the die test, all the way to the deployment, which is really can be associated with the end-to-end test, because the number of tests you're going to perform on a die, on a wafer to parametric test is really associated with the different steps. So let's pursue along this line and see how much of that correlation we can we can really find. And as you said, it didn't happen overnight. It didn't happen from Sunday to Monday morning. So can you give us a bit of history and how you got there over time?
Sure. So if we look at the timeline, it's in the 1950s-ish where we saw the initial emphasis on testing the software. Initially, it was mainly done through debugging. So you write the system, you write code, and then you let it crash, and you debug, and you see what's happening, you try to improve it, and you try again. Then a bit later on, it became, the mindset was, let's demonstrate that the software actually works. So you want to, the people started to do tests that were not necessarily automated to show that the system is doing what it is supposed to be doing. And then later on, people realized that maybe showing that it works is fine, but what about finding what doesn't work? So the testing moved into a mode where let's try to break that software. So the destruction phase. So let's try to see where are the cracks and let's fill those cracks. And as you can imagine, the various systems became much more resilient and solid. And then moving forward with all those good techniques of demonstrating that it works, as well as trying to find the cracks and making it break and fixing it and showing that it's been fixed, we found ways to evaluate and measure this quality and keep track of it as the software evolves. So you can see if there were some regression into the system for things that were working and no longer working, performance, and all that kind of different testing aspects that you can imagine. And then starting end of the 80s, beginning of the 90s, we got into this prevention phase where it's very proactive. We're looking at how can we predict that the quality will be there or will not be there. And as you can imagine, we are in that phase right now. And there's a lot of innovation with we can see the speed at which new system and software systems get deployed into the real world. So we've seen different key milestones in this era. So some key milestones that really changed the way we test software. Like around 2002, there was this technique developed called test-driven design, which is you writing the code before the code for the test before you actually write the code. So when you start writing the code that will make the test pass, necessarily your code will be designed in a way that it's testable because you wrote the test previously. So this whole mindset about writing code that is designed for testability rather than finding ways after the math to figure out how to test this black box. So that was a key changer. That led to higher level kind of tests, so domain-driven design testing for user acceptance tests, where some language have been developed so that people, less technical people, not necessarily coders, were writing the test intention or the quality intention in some kind of domain-specific language, and that would translate into actual testing of the system. But that is more at the higher level of the pyramid that you saw, the system testing or the end-to-end testing, which is a bit more expensive, obviously. So another big key milestone was in 2011 when Netflix open sourced their system called Chaos Monkey. And that system, through software, was actually, and is still actually, simulating that a full data center could blow up, or that a data cable would be pulled out of a machine, or that a disk would explode, or whatever kind of catastrophe you can imagine. And they are doing this in production since 2011. So you can imagine that if you're confident enough that you can simulate catastrophic failure in production without impacting too much the customer experience, that you've done a lot of work prior to that to enable this. Again, moving and shifting the quality to the earlier stage of the development so that it's not expensive when it actually fails in production for real. And then if we look just at last year, Amazon reported about 23,000 deployment of software per day. And as you can imagine, if Amazon goes down for maybe a second or two, they're losing millions of dollars. So they don't want the systems to fail in production. So you can imagine where the software testing is today and how much the developers and the product managers are very confident that whenever they make a change and deploy it into production, it's going to be rock solid. So again, you don't want this to fail in production. So moving the quality and the cost of quality to the left of the process.
Okay, so if we apply this, so if I take the same reasoning that what you're mentioning, and now we have the different steps, for example, that we're seeing here of transceiver manufacturing, from the design phase really to the issues that would be found by the customer. So applying the same thinking of adjusting our designs or having a feedback loop in our process to track or identify those failures as early as possible is really how we're going to be reducing the cost of the quality, the cost of getting quality components. So if we apply this to our process, and coming back to the transceiver testing, where we have multiple players, where we have multiple steps in the manufacturing and deployment process, there is data coming out of those different tests. Could be good quality data, as we've seen from customers. They typically gather the data properly. The problem, as I've mentioned earlier, is there's no real feedback loop or any automatic feedback loop that can be done because of the sequence of events, because of how the things are done. So is there any way, and how can we do this, in terms, can artificial intelligence, or are there means, what has been used by software to get to that point of getting some kind of automated feedback loop in the process?
Yeah, it's a good point, Francois. So we pretty much all steps in the process is probably gathering data, but this data is, if it's not used there, it's very hard to see the value that's hidden into this data. So when we look at the overall ecosystem and the footprint of all this data across all the steps of the process, either building the component, testing that component, it could be unclear what are the relationship, and this is where AI and machine learning can come to the rescue. So there's the process data itself, so about the machine manufacturing the element, but also testing that element at any point in the system. But there's also all the external data, the context data. So who's the manufacturer of that machine? When was the last maintenance? What's the weather outside? The full supply chain getting to you, like just getting that silicon, that wafer initially. What's the history of this? And today, only a very experienced person using their gut feeling will say, you know what, I've seen this in the past and I think this is going to happen. I think it's going to fail later in the process because I've seen it in the past. Well, machine learning can really help with this. It can do relationship and correlation between different pieces of data at the fifth, or the sixth, or the nth level of interaction, something that the human mind just can't comprehend at some point. And the kind of thing we can look into the future, and it's been proven in manufacturing already, that you can predict very early on that something will fail later down the process. Even though everything seems to be green and fine in the test and the data looks normal, there are ways to predict that it's going to fail later on in the process. So again, using AI, there's a possibility to shift the quality to the left and catch errors before they happen, and even before we believe it could be happening. So we're talking a lot about data here, right? And usually, in what I've seen in my experience, and it's true for all the industries, the data is like the precious. It's my data. I don't want to share it. It's like if I share my data, people will learn about my flaws, and it's going to be I lose my competitive advantage and everything. Well, what's been demonstrated, but the industry still has to be educated on that. It's not about the data itself. It's about what you extract in terms of information, understanding, and knowledge, and what you do with that. Okay, so some techniques that are actually in production on many systems, either consumer devices, consumer software, or B2B systems, especially in manufacturing, supply chain, and the financial services industries, is the transfer learning. So what you see in this picture here is like an AI or an artificial intelligence model is actually a blueprint, and then you need to train it. It's like it's a free mind. It's like it understands nothing, but it knows how to understand things when you start feeding it data. So if you take this blueprint and you train it on your own data set, and your competitors train it on their own data set as well, they'll get a very limited view and very biased view of the world. Now, if we get more and more of this data together, and we pre-train a model with all this data, with more variety, less bias, more data sources, better correlation, then when you start using this model in your context, it's going to specialize itself into your own context. And you'll get less biases because it's been pre-trained in a much greater world. You can see this as just yourself, as a very experienced person. When you get into a new job or a new employer, you can apply your experience, your knowledge with the real day-to-day activities and challenges that you see in your new job. You come with your experience. So you can see transfer model as a way to bring in an experienced person in your reality that will be able to act on your own data. And then we talk about very many sources of data that could seem to be unrelated. So how can we make use of this? Well, feature learning is something that is used, and we don't necessarily realize it, but it's an AI, an artificial intelligence model that will work on trying to identify what are those data points that we call features or hyperparameters that will actually have an impact on the decision or the quality of the decision or the certainty of the decision in the end. So it's a parallel training of the model and experimentation. So you have an automated learning behind that will keep improving your model. And again, if we don't democratize the data, this is way overkill. If you consider even a big manufacturer or a big producer, in my past in the supply chain, even Walmart, which is by far the greatest and biggest retailer in the world, realized that even if they use that kind of feature learning on their own data, they are biased by the kind of customers that they have. So again, the democratization of data is very important, and it's not about your specific data, which is a drop in the ocean of knowledge. It's about what you do with the understanding of what the AI model will give you.
Thank you, Gabriel. And really to conclude before taking questions, is really one of the things that we mentioned early in the discussion is how people are protective of their data, how they collect data in a I wouldn't say passive way, but you get the data, you store it, then when you have time, you analyze it. There's no automated feedback loop, and when you do it on in your own little world. So really, one of the important point here, I think, to understand is if the industry, if the different players in industry find a way to share the data they have, to increase the level of quality of the data they have, then we can bring learning models, machine learning into the equation where everybody will be able to get the most out of this and really reduce the quality cost and increase the reliability as a whole in the industry. So this is what AI can bring that in the equation, which in our opinion is completely new into what we do from a hardware perspective and really with transceivers and silicon photonics process. So at this point, I'd like to open the discussion and open for questions. So Falk, I don't know if you have any questions coming from the audience, and feel free, anybody attending, if you want to use the chat again to ask any questions or comment, please feel free to do so. We'll answer as much as possible.
We got indeed some questions, Francois. The first question is, how advanced is EXFO in the development of artificial intelligence? I think that's a question that goes more to Gabriel than to you, Francois. He said already a few things about AI, but maybe the question is about what specifically EXFO is doing in that area and is planning to do in near and long-term future.
Yep, it's a good question. So obviously, we would not be talking about AI if we would not have an opinion in some projects on this. So as you may know, EXFO has an internal team dedicated to future-looking and advanced applied research, and we made a lot of progress on a few projects, especially in our service assurance business. But we're starting to get access to this data, right? As I mentioned, access to data is the key challenge. From my previous life, even building AI solutions in different domains, like the key challenge is access to data. But with the help of the different teams in EXFO and some partners and customers, we're getting access to data, and we're starting to see the kind of correlation I'm talking about. We're working with a customer on a project like this in order to kind of predict the impact of some changes in their manufacturing processes using the data that they have and artificial intelligence that has been developed internally.
Yeah, that brings us already to the next question. Is EXFO using AI learning to optimize its own development and manufacturing? You said it, Gabriel. We are benefiting from the data and from AI also ourselves, but maybe you have some more comments on that. So
yeah, we're working with the internal teams to get access to the data and structure it, and everything around privacy has to be considered, right? And the challenge that Francois expressed initially, we're gathering this data at every step of the process, but it was not used until now. So it's a bit unstructured, and working with the teams leading into the advances in the research, the applied research I was talking just a bit before. We're definitely on that path. It's part of our strategy. But AI is not something that happens on a Sunday to Monday morning, as we were saying. It's something on the long run, but we're working on that journey. And obviously, it's part of the technology and product strategy.
Very good. Yeah. And another one, maybe more for you, Francois.
Yes.
Are the EXFO instruments like CTP10, etc., are they compatible with the manufacturing processes described in that presentation? I think CTP10 is just an example.
Of course, CTP10 is just an example, but if you look at the process and during parametric testing, you could be talking about OSAs, the power meters, transport analyzers, BERT scopes, whatever the type of equipment you will need along the way. I would say to make them compatible with such process is really to make sure that the test results, the data you collect can be used in some way. So it's really the key, and I think we've mentioned it a couple of times already, but getting access to quality data is really what's going to make a difference between being able to use those results and optimize the data and not being able to do so. So in a way, definitely yes, and our equipment, and we've been doing some storage, cloud-based storage, for example, to be able to share data. We've been doing that and offering that for multiple years already. So we're building on the experience we've gained over the last 30 years and improving. But the key part is data, and yes, of course, everything that we have, every new instrument that we have, we also make sure that we have all the data, not only on the results they're getting in terms of measurement, but we've also started implementing in some of our instruments some telemetry information as well, to be able maybe even to push that a little bit further to predictive maintenance of your test instruments in production as well. So we're pushing that a little bit further down the road as well.
Yeah, an important topic, predictive
Yes.
maintenance. Yeah, absolutely.
Yeah. Okay. Well, thank you everybody for attending, participating to the discussion. I hope it was useful. Thank you, Gabriel, for sharing your experience on the software side with us. Thank you, Falk, for helping us with the question. So on that, just would like to remind everybody that there will be 3 more test talk sessions in the next 3 weeks, happening on Thursday, same time, same day. Make sure to attend those and register to those other sessions if you've not done so already. Thank you.
Thank you.
Bye-bye.
Bye-bye.